Welcome to the massive open online course on Aspen Plus. In today's lecture, we are going to perform a case study on CO2 sequestration using amine solution. In the said case study, we will come across various features which are very important in chemical process industries, and from the perspective of Aspen Plus simulation, these are very important to learn properly because many a times they pose a serious problem while arriving at a convergence. For instance, we will come across the recycle loop. Recycle loop poses serious bottlenecks in arriving at a convergence. Moreover, we will deal with the electrolyte systems. And in electrolyte system, the charge balance is an important factor. So many of the simulations, they fail to converge just because the lack of charge balance. Then we will deal with the heat recovery, because in many of the simulations that I have shown so far, there we use the condenser where we release heat, and we use reboiler where we need heat. But it is possible for us to use the heater and cooler in such a manner that we can recover maximum amount of heat possible from any of those streams, and we can suggest substantial savings on energy cost. Then we will learn about the makeup stream. Makeup streams are used when some of the chemicals are involuntarily lost due to the vapor outlet, or for that matter any of these outlets from the process, and we do not want to lose them. But such chemicals need to be replenished in the system in order for the system to run on mass balance. So we use some kind of makeup stream that supplies the components which are otherwise lost through the vapor outlet or liquid outlet from the process. Then we will learn about the Microsoft Excel calculation. Till now, wherever we had to perform certain customized calculation, we used Fortran. We used Fortran coding. But today we will learn how to do the same calculation through Excel coding, because sometimes the Excel coding is far convenient to use in Aspen Plus. And today we'll also learn something about hierarchy model. Because hierarchy models are very efficient in order to compartmentalize the entire flow sheet into various small compartments so that the flow sheet looks cleaner and it is easy to navigate through the entire flow sheet. So we are going to learn all these things through this case study. So let us go to the case study and see how we can do it. So this is the case study on CO2 sequestration using aqueous amine, and it contains an absorber stripper process which operates at atmospheric pressure. So in the very beginning of the problem, they say that the entire process operates at atmospheric pressure, so there will be no change in pressure anywhere, either in absorber or stripper or heat exchanger or flash, whatever we use, we do not need to think about the pressure. They will all be at atmospheric pressure. Okay. Now, the amine composition which we are going to use, that has 45% of MDEA and 5% of PZ. MDEA means the methyl diethanol amine. Okay, so this is MDEA. And PZ is piperazine. So this is a blend of two amines, MDA and piperazine. So this is the amine solution. So we have 45% of MDA and 5% PZ. Rest, obviously, it will be water because it is an aqueous amine solution. So it is water. Now the problem begins with a gas stream whose flow rate and temperature has been given. And obviously the pressure has not been given because already we have said that entirely it operates at atmospheric pressure. So pressure is not mentioned again. We will assume that everything at atmosphere. So a gas stream to be freed from CO2 contains 72% nitrogen, 11% oxygen, 5% CO2, 1% argon, and rest water vapor. So we have 72, 11, 5, 1, and water vapor. Water vapor will be 100 minus 72 minus 11 minus 5 minus 1. That counts to be 89, right? Total 72 plus 11 plus 5 plus 1. So it is 89. So water vapor will be 11%. So there will be 11% water vapor. Now all the fractions are on standard volume. So it is volume percent, standard volume percent. Okay. So the gas stream is wet flashed at 40 degrees centigrade. So we will use a flash by mixing with a water stream of 50 kg per second and 30 degrees centigrade before it is fed into the absorber from the bottom. So we will have a flash tank like this. So there we will have the gas stream. The gas stream will enter the flash tank, and the gas stream's flow rate has been given 15 kg 95 degrees centigrade. So we will have 15 kg and 95 degrees centigrade. It will have 72% of nitrogen and other things. So it will be wet flashed. That means some water will come. It will mix with this hot gas, which is at 95 degrees centigrade, and it will cool down. Okay, so there will be a mixing between this water and the gas stream. And this will go to a absorber. That's what it says. As it says here, you can see the gas stream is wet flashed at 40 degrees centigrade by mixing with the water stream before it is fed into the absorber from the bottom. So we are sending it from the bottom of the absorber, and then an amine stream typically 40 kg and 40 degrees centigrade. Why it is called typically? Because we will use a recycle stream later. So there the ultimate temperature and the flow rate might change. So it is said typically 40 degrees centigrade and 40 kg per second of flow rate is fed from the top of the absorber. So we will have it from the top of the absorber. So here the amine is poured into. As amine, we have said it is 45% of MDE and 5% PZ. So this is the amine. Then CO2 free gas is released from the top of the absorber, while CO2 rich amine leaves the absorber from the bottom. So we will have, so this is the gas which is free from CO2 because CO2 has been absorbed by the amine, and rich amine is released from the bottom of the absorber. Okay. Then this absorber has 10 theoretical stages. The CO2 rich amine is fed to a stripper with the following specification. So we will have another stripper over here. So this is our stripper. Okay. So this is the stripper, and it has the following specification. It has 10 stages. The feed stage is 2. The second stage is the feed stage. It has partial vapor liquid condenser, which is maintained at 40 degrees centigrade. The reflux ratio and reboiler duty has been given. Then the problem statement continues. The rate-based calculation and the choice of packing needs to be done by the designer. So here it is saying that it is not an equilibrium calculation that we have to do. We have to rather perform a rate-based calculation. And in order to perform the rate-based calculation, we have to design the packing material. We have to design the diameter and the height of the column and many other things. So these are left to us, the designer. How to design that we have to fix. They are not suggesting anything from their side. Now the CO2 rich vapor is released from the top of the stripper while water rich condensate is recycled back to the top of the absorber. So what happens? Once this is fed into the stripper, there will be a reboiler over here, there will be a condenser over here. So the reboiler will provide heat, and as a result the CO2 will be dissolved and it will release from the top. So in other words, as it is said that it is having a partial vapor liquid condenser, so there will be a vapor distillate and liquid distillate as well. So here it is said the CO2 rich vapor is released from the top of the stripper and water rich condensate is recycled back to the absorber. So we have two condensate over here. One is this one. This is the vapor distillate. Another will be a liquid distillate which will be recycled back to the top of the absorber. Okay. On the other hand, the CO2 lean amine stream is released from the bottom of the stripper, cooled down to 40 degrees centigrade before it is recycled back to the absorber. So the CO2 lean amine is released from here because it is the reboiler. Reboiler provides heat. As a result, CO2 is released from here. So this stream becomes CO2 lean. There is less amount of CO2 over there. In other words, we can say that amine has been regenerated. Okay, it is a lean amine. Then this lean amine is again ready to absorb more CO2 from the gas. So it is recycled back to the top of the absorber. So here we will use a kind of mixer. Okay, so we'll mix the stream with the inlet, whatever the amine we are passing through. Okay, so this is the recycle stream, and this stream will be very hot because it is coming out from the reboiler, and this stream is coming at 40 degrees centigrade, right? This is coming at 40 degrees centigrade. So we have to cool it down with a cooler. This will be a cooler which will reduce the temperature from whatever it is to 40 degrees centigrade because the temperature of lean amine is 40 degrees centigrade, which is going into the absorber. The heat lost by the lean amine is used to preheat the rich amine. That means whatever the heat that is being lost over here, we are not going to lose it permanently. Rather, we will preheat over here. This stream is going into the stripper. So we will use this heat over here to preheat the stream so that we have less load on reboiler. Okay, so some kind of heat integration or energy savings is possible over here, right? Then what it says, the water and amine being lost along the vapor outlets of both the columns are replenished through the makeup stream added to the absorber. So what are the outlets of the process? One is this gas outlet from the absorber and CO2 outlet from the stripper. So these are the only two outlets, and both of them are gaseous outlets. They are released from the system. There is no other outlet. All the streams we have recycled. Okay, so these are the only two outlets. So through these outlets, some amount of water and amine will be lost through these gas outlets, and they needs to be replenished. Otherwise, there will be no mass balance of the amine and water. Okay, so that is the makeup stream that will pass through. So we will use a calculator over here, and this calculator will calculate the amount of water and amine that is being lost through this vapor outlet, and only that amount will be sent through the makeup stream over here. And that calculation we will use using an Excel sheet. Okay, and then finally, after everything is done, along with the convergence of the solution is achieved, I will show you how the hierarchy model can be implemented over here. Because the entire operation, we will see there is only one inlet. Rather, there are two inlets, makeup amine and the gas flow rate. And there will be two outlets, two vapor outlets. All other things are internally recycled. Okay, so we can create a kind of enclosure over here, the entire thing, and this we can put it into the hierarchy so that the entire process is engulfed within this particular hierarchy box, and the simulation becomes cleaner and easier to read. How we will do, we'll learn later. Now, the property method, we will use Elek-Inertial property method and Peng-Robinson property method. The reactions are given in the next slide. Perform the simulation. Okay, so let us go to the next slide to see the reactions. Now there are 5 equilibrium reactions. Okay, so these are the 5 equilibrium reactions. Reacting phase is liquid. The concentration basis is mole gamma. In case of first two reactions, the equilibrium constants are calculated using the Gibbs energy. Okay, so these are the first two reactions. The equilibrium constants are calculated from Gibbs energy, while the equilibrium constants from the other 3 reactions are given as this. So this is for equilibrium reaction 3, this is for equilibrium reaction 4, and this one is for 5. And these are the kinetic reactions. Altogether there are 8 number of kinetic reactions, and these reactions also, they are liquid phase reaction, but the concentration basis is molarity. In the earlier reaction it was mole gamma, but this reaction it is molarity. The power law kinetic expressions are given in the next slide. So these are the kinetic factor equation. Okay, so for all the reaction number 6, 7, 8, 9, 10, 11 up to 13, The K values are given as this and E values, they are like that. So we have to choose calorie per mole as the unit of activation energy, and accordingly R will be chosen. And here the T is in Kelvin. Now let us open the Aspen Plus window and develop the flow sheet and perform the simulation. Okay, now let us first insert the components. The first component, we will use the MDEA. Okay, MDEA. And piperazine, we will search for piperazine. This one. So just rename it as PZ. Gas stream has CO2. We will write it over here, CO2. Then we have nitrogen, oxygen, argon, water. So nitrogen, oxygen, argon, water. And we will have some ions also because it is an electrolyte system. The ions we will get over here. So we will gather these ions also. So we'll have H3O plus. We will have OH minus, HCO3 minus. All of them are conventional ions. So if you write it in this fashion, it will take CO3 double minus, then PZH plus, HPZCOO, PZCOO minus, MDEA plus, okay. And we will go to the kinetic reactions. There we have a few. These are already taken. We have not taken PZCOO double minus, right? So we will take PZCOO double minus. Okay, this is not taking, so we will use -2. Yeah, now it is taking. Now we can rename it. So actually, in the Aspen Plus data bank, this component is regarded as PZCOO -2. Okay. So if you write PZCOO minus minus, it will not identify, unlike this CO3 minus minus. So you have to write PZCOO -2, then bring up the component as it will identify, and then you can change the name of the component for your own convenience. Yeah, I think we have taken all of them. There are 16 components. Okay. Now we have to choose the methods, and the methods are Elek-NRTL and Peng-Robinson. So let us choose the Peng-Robinson and Elek-NRTL also. So both the methods we have chosen, and we have to get them. Okay, so we will press next. This one is calculated. NRTL1 should be calculated. Then PRKV1, VLCLK, and then 4 electrolyte pairs. Okay. Now it is ready to run the simulation. Okay. So the property run is done. Now go to the simulation. And before going into the simulation, we can set some property, because we have to see how much CO2 we are recovering in any of the streams. So we will watch the stream flow rate as well as the CO2 flow rate inside that stream. How much CO2 is being carried inside that stream. So for that, we will say the mass flow rate of any component. So this is the mass flow rate of a component in a mixture. And we will take a qualifier. We will take total, because we want, in a mixture where both vapor and liquid phase are there, we want to count the entire amount of CO2 that is there in either vapor or the liquid phase in that stream. So we'll take total component of CO2. Okay. So that's exactly what we will check. Now come to the flow sheet. Okay. Now we have to develop the flow sheet. Now we'll refer to this. This is the thing. So we'll have a flash tank here. Then we will have one absorber, one mixer. There will be a heater. There will be a cooler over here. There will be another column. So both of them will be rad frac column. So this is one rad frac column. This is another rad frac column. This will be an absorber. This will be a stripper. So that is the total thing. So we'll go step by step. First, we will take a flash tank, simulate it. Then we'll go to an absorber, simulate it. Then we will take the stripper, simulate it without the closed loop. We will simulate in the open stream, and then we will close the loop. We will add a makeup stream. Okay. And then the simulation will be complete. I mean, if we get a convergence, we will be lucky. And if we do not get convergence, we have to keep trying with various things, because the rate-based calculation is open to us. We can choose any number of ways that we can try until unless we arrive at a convergence. Okay. So let us do in that fashion. First, we will take a flash tank. So this is our flash tank. Okay. So flash tank, this is the inlet. There will be another inlet, which is water, because it is wet flash. So this is gas stream. So we will have another stream over here, which is an outlet stream. And this is the stream which is going out. So this is the gas stream. We'll call it raw feed. And this we'll call absorber feed. This one we'll call flash water inlet. And this one we'll call flash water outlet. Okay. The raw feed, we have to mention what is the raw feed. Raw feed is The temperature is 95 degrees centigrade. The mass is 15 kg per second. And the composition we have to write as standard volume fraction. Okay, so all the fractions are on standard volume. It is 72% nitrogen. So nitrogen 0.72, oxygen 0.11, 5% carbon dioxide. So this 5% we have to remove from the stream. 1% argon. So total it is 89%. So rest of them will be water vapor. So water vapor will be 0.11. So that makes it 1. Okay. And the pressure is 1 atmosphere. Okay. So this is the raw feed that we have. And the water inlet for the flash that comes at 40 degrees centigrade. Right? So this is 40 degrees centigrade, 1 atmosphere. No, it is wet flashed at 40 degrees centigrade. So the flash tank temperature is 40, but water stream is at 30 degrees centigrade. So it is 30 degrees centigrade and 50 kg per second. So it is 30 degrees centigrade and 50 kg per second. And it is totally water. So we do not write anything over here. Rather, we will write the mass flow kg per second of water. It is 50 kg per second. Okay, that's how we define the flash water in, and that will be used to cool the raw feed and specify the flash tank with 40 degrees centigrade. The pressure is 1 atmosphere again. Okay, so this is very simple. You can just run it. Okay, so the results are available, nothing to worry about at this stage.